What if instead of a resistor inductor circuit, we have a inductor capacitor circuit? We also call this an LC circuit for their abbreviations. The behavior of this circuit might surprise you. Here in this picture, if we start off with a capacitor charged so that the top plate is positive, bottom plate is negative, and we've closed a switch to connect it to this inductor, now the positive and negative charges can get together. They just have to go through the inductor. The inductor initially fights that and doesn't want them to move through quickly at high current, so it takes a while for them to get around. The inductor finally has an established current through it. By the time the capacitor has discharged, there's still a current in the inductor and it doesn't want to stop now that it's gotten established. So it keeps going and effectively drains more positive charges out of the top and puts them on the bottom. So by the time the current finally stops, the capacitor is charged the other direction. Then the current starts back that way. And of course the inductor fights it, but eventually it establishes a current. And by the time the current is stopped, we're back to where we were with a charged capacitor in the original configuration. The time here for this to happen once is called 1 period, and it's capital T in this picture. You can see a plot of charge on the capacitor at a peak when we start and current on the inductor being 0. Then by the time charge gets to 0 on the capacitor, current is a peak one way in the inductor, and they just keep going back and forth like that. You can tell one of these is a sine, one of these is a cosine, or one of them's a cosine, one of them's a negative sign, however you want to think of it. This circuit, if there's no resistance, this will oscillate forever and ever. It's called an oscillating circuit. Sometimes it's called a tank circuit. And it's what used to be used to make radio receivers. So this period is related to the frequency that this thing is tuned to pick up. And our frequency, of course, is 1 over period, and we'd measured in hertz or inverse seconds, as they're the same thing. F tells us how many times per second we'll have this oscillation, and we can solve for it as 1 over 2 pi times square root of LC. If we have, for example, a 5 millihenry inductor, 10 microfarad capacitor, and put them together, they'll oscillate at a frequency of 712 hertz. Now, just like we can't really have a mass on a spring on a frictionless tabletop sliding back and forth forever, there's no such thing as a system that's just an inductance and a capacitance. We'll have wire connecting them. The leads on the capacitor will have some resistance. The wire making up the coil in the inductor will have some resistance. So there's going to be some R there, and now we would call it an RLC circuit. So we still pretend like we have perfect capacitors and inductors, and we add this perfect resistor. Now if we charge up the capacitor and put it in this circuit, it's going to work like it did before, only the size of the oscillations will get smaller with every trip. So instead of just going back and forth forever, it'll still go back and forth, but this green dot here shows you the exponential function. That's called an envelope. That's what's gradually killing this oscillation. So it'll shake back and forth, the charges from one side of the capacitor to the other until it finally stops. If we want the mathematical formula for what this looks like, the frequency where it happens now is a little bit different than it was without the resistance. So the frequency changes a little bit, and the oscillations happen at this new frequency, omega prime, and then they're damped by this exponential term. This, by the way, is exactly what it looks like when you have a screen door with a spring on it and a shock absorber in it, like most of them do. You get this same kind of damped oscillation. The damped harmonic oscillator is really big in first semester physics. We can transfer all the stuff from there directly to here. And if we have the L and the C at resonance to some particular driving force, we'll get a much larger result than we would expect otherwise. This is the same as pushing someone on a swing. It's easy enough for your pushes to match the natural frequency of oscillation of the swing, and if you do that, you can get someone going very high up without a whole lot of effort. Now we can find a correspondence between this and the mass on the string with the shock absorber, mass on a spring with the shock absorber, by putting them together like this. Our sort of fundamental thing last semester, we had position, velocity, acceleration. This semester it's charge, current, which is change in charge over time, and then change in current over time. In the mass and spring and shock absorber setup, K is the spring constant, B is how sort of sticky the shock absorber is, and M is the mass. Here we have 1 over C, which is kind of like the spring, R, which is like the shock absorber, and L, which is like the mass. So we can find sort of an equivalence between these things on the same line. Now, if we look at the things at the ends of the arrows, for example, X and K, we know that Kx is the spring force. If we look at Q and 1 over C, Q over C is voltage. What about the red arrow here, V and B? Well, that's the damping force from the shock absorber. I and R is the voltage associated with the resistor. Finally, the brown arrow here, A and M, we know MA is a force, and L and changing current over time, that's the voltage produced by the inductor. So we see there's a pretty direct correspondence between these things, where the things on the left we end up talking about forces, the things on the right we end up talking about voltages. This is where they get that otherwise ridiculous name of electromotive force. It's like a force when you're talking about moving electrons instead of masses. This L acts like M because M doesn't like to see velocity change. L doesn't like to see current change. A large value of X will give you a strong spring force. A large value of Q for a particular capacitor will give you a large voltage. You can see all the things pair up just like they did last semester, and a mathematician would say there's no difference in these two problems. Now, your book actually spends a section in one chapter on series RLC circuits that have a AC driving force. In other words, plugging this into the wall. So we have a little sinusoidal driver here. We're not going to do that in this course, and the reason is there's too much other stuff for us to emphasize there to spend time on this. This is a little bit, this is a lot more appropriate for the calc-based course, where they, if they're going into electrical engineering, they need to see that kind of stuff. There are some general ideas here, though, that are worth knowing. One, inductors and capacitors can both slow down the current in an AC circuit just like resistors do. One big difference is this ability to slow it down, and we call it reactance instead of resistance in this case, but it's still measured in ohms, is frequency dependent. For example, in a circuit with a battery, so we could consider that to be an AC source with a very, very low frequency since it never changes, a capacitor will charge up and stop the current, so it's like an infinitely large resistor once we charge it up. On the other hand, if we have an inductor in the circuit with the battery, like in the RL circuits we just saw, we know that the inductor essentially disappears from the circuit after the current settles down and stops changing. So the capacitor acts like a broken circuit, and the inductor acts like a short circuit, just a wire. At very high frequencies, though, we know the inductor hates to see the current change, so the EMF that it produces, which is proportional to how fast the current changes with time, will be very large for a high-frequency AC source. So in other words, a very high-frequency AC source with an inductor in the series circuit, this will limit the current to practically nothing. As the frequency goes up, the inductor fights it harder. The capacitor, on the other hand, sort of disappears from a high-frequency circuit. If you want a way to kind of understand this part about the capacitor, we remember that at high frequencies, the electrons change direction very often, very quickly. We know that the actual speed of the electrons, which we call the drift velocity, is millimeters per second or less. So if their max speed is millimeters per second or less, and they're changing direction millions of times a second, how far will they ever go from their initial position? Not very far at all. They'll hardly see any of the rest of the circuit. So practically all the electrons in an RLC circuit will never even see that there's a capacitor there if it's high frequency. That may help you keep this in mind.